Have you ever wondered why the sky is blue or how rainbows form? These everyday wonders are more than just beautiful sights. They are windows into the intricate dance of light and matter. The answer lies in the fascinating ways light interacts with matter, dispersion and scattering. These processes are fundamental to the way we perceive the world around us, influencing everything from the colors we see to the clarity of our vision. These phenomena, while seemingly simple, paint the world around us with vibrant colors and breathtaking optical illusions. Imagine a world without the rich hues of a sunset or the magical appearance of a rainbow after a storm. Dispersion is like separating a deck of cards, each card representing a different color of light. When light passes through a prism, it spreads out into its constituent colors, much like how a deck of cards fans out when shuffled. Scattering, on the other hand, is like throwing a handful of marbles onto a bumpy surface. The marbles bounce off in different directions, just like light scattering off tiny particles in the air. This scattering is what makes the sky appear blue during the day and gives us the warm hues of sunrise and sunset. These two phenomena, though different, are responsible for a plethora of visual wonders we often take for granted. From the shimmering surface of a lake to the twinkling of stars in the night sky, dispersion and scattering are at play. In this exploration of light's journey, we'll delve into the science behind these phenomena, understand their mechanisms, and uncover the captivating ways they manifest in our everyday lives. We'll see how scientists use these principles to create technologies that enhance our vision and even explore the universe. From the blue sky above to the twinkling stars at night, these interactions of light shape our perception of the world. They remind us of the beauty and complexity of the natural world. Prepare to be amazed by the captivating dance of light. As we journey through this exploration, you'll gain a deeper appreciation for the science that illuminates our world and the wonders that light can create. Imagine light as a wave, not unlike the waves you see rippling across a pond. These waves move in a rhythmic pattern, creating crests and troughs as they travel. Just like water waves, light waves have different wavelengths. These wavelengths determine the properties of the light, including its color and energy. Each color of light, from vibrant red to deep violet, corresponds to a specific wavelength. Red light has a longer wavelength, while violet light has a shorter wavelength. This range of wavelengths is what we perceive as the visible spectrum. Dispersion is the phenomenon where light gets separated based on its wavelength. When light passes through a medium like a prism, it splits into its constituent colors. This happens because the speed of light changes as it travels through different mediums. In a vacuum, light travels at its maximum speed, but in materials like glass or water, it slows down. Think of a car driving on a paved road versus a muddy field. It slows down on the mud, right? The same principle applies to light as it moves through different substances. Similarly, light slows down when it enters a denser medium like glass or water. This change in speed causes the light to bend, a process known as refraction. The amount of slowing down, however, is not the same for all colors. Each color of light bends at a different angle due to its unique wavelength. Red light, with its longer wavelength, slows down the least. This means it bends at a smaller angle compared to other colors, while violet light, with its shorter wavelength, slows down the most. As a result, violet light bends at a larger angle. This difference in speed causes the different colors of light to bend at slightly different angles, leading to the separation of white light into its constituent colors, a spectrum. This is why we see a spread of colors when light passes through a prism. This beautiful separation of colors is what gives rise to the mesmerizing spectacle of a rainbow. When sunlight passes through raindrops, it gets dispersed into a spectrum of colors, where sunlight is dispersed by raindrops acting like tiny prisms. Each raindrop bends the light at different angles, creating a circular arc of colors in the sky. This natural display is a perfect example of light dispersion in action. A prism, a simple triangular piece of glass, beautifully demonstrates the phenomenon of dispersion. When white light enters a prism, it slows down and bends, a phenomenon known as refraction. As we learned, different colors of light bend at slightly different angles due to their varying wavelengths. Red light bends the least, while violet light bends the most. This difference in bending spreads out the colors like a fan, creating a spectrum of colors emerging from the other side of the prism. This simple yet elegant experiment reveals the hidden colors within white light, showcasing the magic of dispersion at play. Prisms are not just tools for scientific exploration. They find applications in various optical instruments, from telescopes to cameras, helping us see and understand the universe in all its colorful glory. Dispersion of light is not just a scientific curiosity, it has numerous practical applications that impact our daily lives. This phenomenon, where light is separated into its constituent colors, can be observed in various everyday objects and scientific instruments. One such application is the spectroscope, an instrument used to identify different elements based on the unique way they emit and absorb light. By analyzing the light spectrum, scientists can determine the composition of various substances, whether they are here on Earth or light years away in space. When light from a star or a distant galaxy passes through a spectroscope, the elements present in those celestial objects leave their unique fingerprints on the spectrum, revealing their composition. This process, known as spectroscopy, allows scientists to decode the light and understand the chemical makeup of stars, planets, and other celestial bodies. This allows astronomers to study the universe's building blocks and unravel its mysteries. By examining the spectral lines, they can determine the presence of elements like hydrogen, helium, and even more complex molecules, providing insights into the origins and evolution of the universe. Closer to home, dispersion is responsible for the iridescent colors we see on a CD or DVD. These discs are not just storage devices, they also serve as a beautiful example of light dispersion in action. The closely spaced tracks on the disc's surface act like a diffraction grating, separating white light into its constituent colors. This intricate pattern of grooves and pits on the disc's surface interacts with light, creating a spectrum of colors that can be seen when the disc is viewed under a light source. As you tilt the disc, the angles of reflection change, causing the colors to shift and shimmer, creating a captivating visual display. This mesmerizing effect is a direct result of the principles of light, dispersion and diffraction working together. From understanding the cosmos to enjoying the shimmering beauty of a CD, dispersion plays a fascinating role in our lives, whether it's helping scientists unlock the secrets of the universe or adding a touch of magic to everyday objects. The dispersion of light continues to be a source of wonder and discovery. While dispersion separates light based on its wavelength, scattering sends light bouncing off in different directions when it encounters particles in its path. Imagine throwing a tennis ball at a basketball. It bounces off in a predictable direction. Now imagine throwing that same tennis ball at a bunch of marbles scattered on the floor. It bounces off in unpredictable directions. That's similar to what happens with light scattering. When light encounters particles smaller than its wavelength, it gets scattered in all directions. This phenomenon, known as Rayleigh scattering, is responsible for the blue color of the sky. But scattering isn't always random. When light encounters particles larger than its wavelength, a different type of scattering called me-scattering comes into play. This type of scattering is responsible for the white color of clouds. Understanding the different types of scattering helps us explain a range of atmospheric phenomena, from the blue sky above to the white clouds that drift by. Have you ever gazed up at the vast blue sky and wondered why it's that particular color? The answer lies in the fascinating phenomenon of Rayleigh scattering. As sunlight enters the Earth's atmosphere, it encounters tiny air molecules much smaller than the wavelength of visible light. This results in Rayleigh scattering, where blue light, with its shorter wavelength, is scattered more strongly than other colors. Think of it like this. Imagine a blue marble and a red marble being thrown at a bumpy surface. The smaller, lighter blue marble is more likely to be deflected in different directions, while the larger, heavier red marble is more likely to travel in a straighter path. Similarly, blue light gets scattered all over the sky, making it appear blue to our eyes. This is why we see a clear blue sky on a sunny day. While Rayleigh scattering explains the blue sky, it doesn't explain why clouds appear white. This is where Mie scattering comes in. Clouds are made up of water droplets and ice crystals, which are much larger than air molecules. When light encounters these larger particles, Mie scattering occurs. Unlike Rayleigh scattering, which is wavelength dependent, Mie scattering affects all wavelengths of light equally. This means that all colors of light are scattered equally in all directions, resulting in the white appearance of clouds. The thicker the cloud, the more light is scattered, making the cloud appear even brighter white. So the next time you look up at a fluffy white cloud, remember that it's the result of Mie scattering, a fascinating phenomenon that paints the sky with its own unique brushstrokes.